Okay, Marcia, you can start.
Yeah, give me a sec. I'm trying to. Shit. I am trying to. Oh, okay. Here it is. Okay. So, hi everyone. Thanks, Hieronimo, for this presentation. So yes, I will be talking about chaotic MEMS, basically. But before going into this, I'm gonna present you a bit of the lab, TIMA, which has nothing to do with DARPA. I work in Grenoble in France. It's a very nice city surrounded by mountains, a lot of hiking to do and skiing, so it's quite nice. But there is also, as far as science is concerned, quite a lot of interesting things, a lot of different labs. Here I name but a few. Actually, there's much more labs in Grenoble, but those, let me put the pointer. Yeah, so those labs, they all have at least one team working on MEMS or NEMS devices, and it's all in Grenoble. So it's very nice city to work in. But so I work in TIMA as a researcher. So TIMA is in two different places in Grenoble, those two pictures basically, and my office is just around there, basically. And so in TIMA, there are many different things that are being going on. Basically 4 departments. One is about fault injections in hardware security. Another one is about RF circuits. Then we have some system level with, for example, parallel architectures. And last but not least, system integration with, in particular, microsystems and MEMS, and I belong to this last category. So as far as MEMS is concerned, actually in TIMA, it's been quite a while. It initiated a MEMS CAP that you might know, it's a MEMS foundry. And more recently, EuroMEMS, a startup at the boundary between MEMS and medical applications. And for the research part, we are mostly working on piezo MEMS, so from energy harvesting to Pmods, that is ultrasonic transducers. I will come back to this last one in more details during this talk. And just FYI, before I forget, we are actually looking for a postdoc. So if you know someone who could be interested in doing some PMUTs for aircraft applications, it's mainly with Airbus, which is the French Boeing, basically. And the point is to make some MEMS-based microphone with a very large acoustic overlap point of 135 dB. And so this will be dealt in TIMA with a collaborator of mine, Libor Ruffer. So you can either contact this person or you can contact me, or maybe Geronimo. I don't know if you can have this through, but whatever. So we have this postdoc position open. So
sure, we can also post it on the website if you want.
Yes, that would be perfect. Thanks.
Yeah.
So when I arrived in TIMA, I brought my own knowledge, which is mainly nonlinear MEMS, and I started to get interested into chaotic MEMS, and that's what this talk is going to be about. So don't worry, there will be nearly no equation, and the rare few are not so important. It will be mostly about figures, graphs, some videos, hoping that you will come out of this presentation understanding a bit better why chaos could be interesting in some MEMS applications. So let's start. Let's start with generation of chaos. In general, where do we find chaos? What is chaos? I think you might have heard the term, but maybe you don't really know what it means. So basically, chaos is a nonlinear phenomena that you can find kind of everywhere as long as you know where to look at it. So here are a few examples. Here is one of the moon of Pluto. Does the video works or yes? I guess yes. So here is one of the moon of Pluto called Nix. So it's rotating around Pluto. It's also precessing around itself. And what people found is that they can't predict this precession for better than a couple of months. And they realize it's because the precession is purely chaotic. Another example that you might know of is the swinging sticks. I'm sure some of you have seen something very similar to this. It's mostly known to be some kind of lossless device, but it's actually also chaotic because you can't predict much and it's always doing something different. Last but not least, the weather. Well, I don't think it requires any comment, but the weather is one of the first chaotic system ever studied. So what makes all these systems chaotic? Well, to have chaos, first, you need complex interaction within at least 3 dimensions. So for example, for this moon, well, Pluto has many other moons and they are all interacting between each other. For the swinging sticks, well, each of the sticks has at least 2 variables. And for the weather, well, thousands of billions of parameters. So that's one thing. The next thing is a chaotic system is non-periodic, which is okay, but it's non-periodic and it is deterministic. And what this means is a pure chaotic system can be predicted for an infinite time. You can really predict everything as long as you know everything about your system. And that's the small issue, because the last property is the fact that chaos is exponentially sensitive to initial conditions. And by initial conditions, I mean exponentially sensitive to any change. And that's the big issue, because if you don't exactly know your system, this small difference at the very beginning will spread and spread. And it's basically the reason why you cannot forecast weather for better than a couple of weeks, because you don't know exactly what's happening on Earth. And at the beginning, it's not a problem. But after a couple of weeks, everything just collapses. And it's the reason why also we will never be able to forecast weather better than a few weeks, because every time you need an order of magnitude better precision in everything. Okay, so from here, we can see already that chaos is between 2 things that we know, harmonic oscillator and noise. So just as an oscillator, it's deterministic. You can predict everything if there is no noise, but it's not periodic. Okay, so why do we care about chaos? What kind of applications? So the first one that can come to mind is random numbers. And here I give an example of Cloudflare that you might know of in US. It's dealing with security on internet, like a big portion of the internet flux is controlled by Cloudflare. And they have these lava lamps. I think you can know. I had one when I was a kid. I was mesmerized by this lava going up and down. Actually, this system is purely chaotic, and we know it's really chaos. And so they have a wall full of these lava lamps, and they have a camera recording it. And because it's a physical chaotic system, it's not predictable. And they use this to feed their algorithm to provide very secure random numbers. Another example is in robotics, where you can see this robot it's facing a slope with some sand, and there is a hole, and basically they developed an algorithm based on this exponential sensitivity to initial condition, so that the robot, without even knowing there is a hole, tries to find a way to go through. Last but not least, this is an electroencephalogram of someone experiencing an epileptic seizure. So for a few seconds, just here. And what researchers found is that during this epileptic seizure, they can really determine that there is a low dimension chaotic dynamics going on. And thanks to this, they say that they can predict the epileptic seizure a few minutes ahead because of what we now know about chaos. So we can predict it will arrive at some point. And so from those two examples, random numbers and epileptic seizure, we can already see that another interesting property of chaos is the fact that it's big. It's big, meaning it's within the signal itself, not like noise, which is ppm or percentage. So chaos looks like noise, but it's large, and that's very interesting for random numbers because you don't have to probe something that is very small. Okay, now that we know why some people are interested, how do we create this? How do we tailor it for a given application? Well, the easiest one is to take just a mathematical expression. It's not because it's chaos that you cannot describe it with some mathematics. So here is one of the few equations. It's quite a simple equation. It's a recursive equation. So you have some x0 and you can determine x1 and so on. And you just have one parameter, r. So let's, for a few seconds, just study this to understand how chaos works. And to study this, we will use this kind of graph where the red line here is just this equation, and then you have this diagonal line. And the way you use this kind of graph is that you start somewhere, and then you just, every time you try to reach the red line. So x0 is here, x1 is there. To reach x2, you just bounce back to this diagonal line, and then you go to x3, and you can clearly see that you will converge to 0. That's for a given r. If we now increase this r, we converge to another value. If we increase even more, we don't converge anymore. We see that we will switch from one state to another, back to the first one, and so on. And if we increase even more, we get chaos. So this very simple equation leads to chaos. It's a mathematical expression, which means that if tomorrow I run the same simulation, I will get the exact same results. And this is not so interesting. What's interesting in when it becomes unpredictable. And to do this, we have to move from mathematics to physical systems, such as electronic systems. And one of the most well-known systems is actually the QR circuit. We can also go into the optical domain with some spatial feedback, some modulation, and this would lead to chaos too. And so those two fields are quite interesting because, I mean, electronically, it's quite cheap. So you can have many applications just because it's quite cheap. Optically, well, you have all the telecommunications, the optical fibers. So this is another big reason to go to optics. But what we care about during this talk is mechanical chaos. And so to have chaos from mechanical structures, what people do usually is to buckle the structure. So in the macro world, it's kind of easy. You take a ruler, you push on both ends, and at some point your ruler will just buckle up or buckle down. But in the micro world, this is a bit more complex. And so what people usually do in MEMS, if you take the example of this Doppler beam, they put electrodes on both ends, and then they put a voltage difference, and they put it so large that the system will buckle. I'm not talking about pulling, it's really buckling. The big issue with this is that it's active. It needs tens of volts all the time. So it's not really good for power consumption. And the other issue is that, well, not a lot of people care about double clamp beam. Most people care about real applications, and few of them concern double clamp beam. So can we make chaos not with double clamp beam, basically? So now I start to go into the MEMS world. I don't think I need to introduce MEMS. Here are just a few examples, a few different applications. My point with this slide is to say that as far as I am concerned, for me, there are two families, either non-resonant or resonant. So of course, you can say that some accelerometers are resonant and back and forth. Here, I just want to highlight the fact that during the rest of this talk, we will only be talking about resonant devices, and that mostly any resonant devices could fall into what you will see. So, resonators. Very quick update, quick 101 what a resonator is. Let's go back to our double clamp beam. It can be described with this. So this is like the last equation that you will see. And so this double clamp beam, if you drive it at low amplitude, that is in the linear regime, well, you will measure some resonance if you're close enough to it. And so from this graph, you can extract resonance frequency, bandwidth. This leads to quality factor, and you have the amplitude related to the force of that you're applying to the system, either voltage difference or magnetic or whatever. So that's the linear system. It's fully described by this equation. Now, if we drive harder the system, we reach the nonlinear regime. And by harder, what I mean, usually what it means is that the amplitude is of the order or larger than the width of the beam. But this nonlinear regime can be reached not only in double clamp beam, you can have it in accelerometers, in gyroscopes, you have it basically everywhere because you're in the micro world, and this nonlinearities just get bigger than in the macro world. So this nonlinear regime, what it means basically is that you will start to have your resonance bending one way or the other. It doesn't really matter, it bends. And what's interesting is that you can describe this fully with just one more term, which is called the Duffing term. It's a cubic term. And what it basically means is that the resonance frequency will shift with the square of the amplitude. But that's not the only thing. As you might have noticed, the curve itself is quite different. And what's very interesting is that you have this hysteresis, which means that if you sweep in frequency upward, you will reach large amplitudes, but if you sweep downwards, you will reach low amplitudes. So don't pay too much attention to this third solution, which physically is not stable. The main point is to say that for a given frequency, you are either at large amplitude or at low amplitude. And people have been using this Duffing regime for many different kinds of applications. Here I just cite a few. So for example, for bit storage or bit flip, because, well, you have two states, so let's make a bit out of it. You can see also that because it's bent, it looks like the bandwidth, the bandwidth of the system is larger. And so people have been studying how they can use this for energy harvesting. And last example, mass spectrometry, where you would have particle dropping on your device. And because of this, you have a frequency shift. Now, if you're here, for example, and that you have a frequency shift, you will jump down to the lower state. And this is a huge amplification of just a tiny frequency shift. So some people have demonstrated some application in the mass spectrometry domain. Okay, so let's go back to chaos and buckled structures. As I was telling you, we could reach, some people could reach chaos with buccal structures because you actually have two states. And this can be described by this double well potential where you have two minima. And so you can switch from one minima to the other. And if you do it with the given rate, given force, everything, you might reach this chaotic regime. But as I was telling you, the Blickland beam is not so useful all the time. But what we've just seen is that with the Duffing regime, we actually have those two states already. And this regime, you can achieve it in any vibrating system as long as you drive hard enough. Again, it can be seen as a double well potential. It's not the same as the first one, but as long as you can switch from one to the other, you might go to chaos. So this is where we start to now look at actual experiments using this device. It's a PMUT, so a piezoelectric micromachine ultrasonic transducer. So basically something that generates ultrasounds. It has been made with MEMS cap. It's made of silicium with some aluminum nitride layer. And so basically the fact that it's piezoelectric, what it means is that as we drive the system through one of the electrodes, here the outer electrode, well, we make the device vibrate because it's released underneath. And as it vibrates, it creates a charge displacement that we detect. So basically, we drive and we measure. And when we drive, we use a standard sinusoid wave and we get this result. So in our case, our PMUTs is vibrating at around 70 kilohertz with a quality factor of about 100. And if we drive harder, we start to reach this Duffing regime and we have this hysteresis. So this is a simulation. In reality, this is what we have. So there is not this third solution, but we can clearly see this hysteresis. And as I was telling you, inside the hysteresis, you have this double well potential, but depending on where you are in the hysteresis, the double well potential is not the same. But what you can see is that you can basically, as you move back and forth, you can reach one state or the other. So you can switch between the two states. And that's the whole idea. We're going to put a modulation in frequency at the very beginning. So basically using that. And doing this frequency modulation will help us to switch from one state to the other. So from the low amplitude to the large amplitude. Of course, the rate at which we do this has to be carefully chosen. If it's too slow, you will just cycle and nothing will happen. If you do it too fast, the system won't have time to respond and it will just saturate at some point. But if you find the sweet spot, it will not have enough time to be at equilibrium. It will be out of equilibrium. And that will create new dynamics. Okay, so that's chaos. Now, it's non-periodic, it's non-reproducible. How do we study it? And that supposedly was characterization. And unfortunately, I realized that I might not have enough time to do both characterization and applications. So I decided to go directly to applications because I think that's what you were more interested in. And if I have time left, I will explain how we characterize such systems. Or if you're interested during the questions also. So let's move to the application. What can we do with such system? And we start with PMUT. So I didn't explain much what a PMUT is for those of you who might not be familiar with. Basically, we have this the same kind of device I showed you. We emit an ultrasound wave, and we can use these waves to detect target and use it as a range finding, because as the wave is propagating and reflected back, the time it takes to do this back and forth gives us basically the distance of the target. And so a lot of people have been working on this. And nowadays, people are even interested in arrays of these devices. I will try to show you that chaos can be interesting for this kind of applications. But maybe before going into this, is there any questions so far? Have I lost everyone? How is it? No answer, everybody's sleeping?
Good so far.
Okay, so let's go on then. Just to make sure that we are on the same page, I wanted to clarify one point. So if we drive something at some pulsation, you look at it under an oscilloscope, you have some sinusoidal thing going on. If you do modulation in frequency, well, the sinusoid will have modulation, that's obvious. But when we apply this to the MEMS, that's when it becomes interesting, because these sinusoids will not be affected much. What's affected is the overall amplitude. So this is the demodulated amplitude that we care about. This is where we have chaos, actually. It's not within the sinusoidal wave. It's within the envelope of this wave. So from now on, I will not show any of this real-time sinusoid pattern. I will mainly show this envelope. Okay, so we have our system, we drive it with a modulation in frequency. And if, in this graph, for example, I start the modulation at t = 0, and you can start to see the amplitude moving around. Now, the first question is, how do we know that this is chaos? Well, it's easy. You just try to redo the exact same measurement. So you park at the same amplitude and you trigger once more modulation in frequency. And you do it once more. And every time what you will see is that for a given time, it seems to be quite reproducible, but after some times it's completely not. And this is really like the forecasting weather. You have some range where you know what will happen, even though it's quite complex. And after some times, you don't know anything at all, because you try to do the best you can to be in the same spot here, but you can't do better than the noise present in your system. So it's kind of a noise. It's a bit more complex than noise. It has more properties, but let's see how it goes when we don't look at the electrodes, but we actually put a microphone to see how well this chaotic wave propagates. And so this is this graph where we have here just the piezoelectric response, and here the acoustic response. And as you can see, I mean, you have some delay, of course, because this is at 25 centimeters, so it takes some time. But apart from that, the overall shape is quite similar. You have those two kind of mountains that are here. You have a big peak that is here, and so on and so on. It's not perfect, but qualitatively, it's roughly the same. Okay, so that's the first test. Next is to know if the beam profile is similar. That is, as you move your microphone around, what do you measure? So first off, in the linear regime, so this is our beam profile in the linear regime, so it's really not nice. So for information, if you consider the size and the frequency, you should not expect any lobe. It should be a pure, nice circle, half circle. It's not the case because we don't have this packaged, and it's not as nice as we would want. So it has some pattern. And if we now move from the linear regime to the chaotic regime, we have some similar profile. It's not perfectly the same, but basically what it means is chaos is not affecting so much the beam profile properties. And what we can look at also is to see how different what microphone measures and what is happening in situ in the device with the piezoelectric measurements. Sorry, that's the one. So this is the correlation between acoustic and piezoelectric at different angles. And basically what you can see is that the correlation is very close to 1 everywhere, even though the beam profile is not really the same and is quite noisy. So chaos, the way chaos is done does not affect at all the properties of the traveling waves. Okay, so what can we do with this? Well, actually, we got inspired from nature, from bats in particular. So I think you will know that bats use ultrasounds to locate prey, obstacles, and things like this. What you might not know is the fact that prey actually tries to fight back, and they try to fight back by emitting themselves ultrasonic waves. And actually, even bats try to jam other bats because they want to have the prey for themselves. And so what they do basically is that if they hear that some bat is trying to hunt, they will send this very broad spectrum pulses to disturb and basically blind the hunting bat. And so that graph is quite interesting. So they use either the red or the blue curve, depending on what they hear. But what's interesting is that when we look at the frequency spectrum of our signal, we have something actually very similar. And that made us think, well, can we jam Pmods with this technique? So basically the experiment is the following. We have 2 Pmods, one used in a regular way and one used in the chaotic regime. So if we just use the linear Pmod to begin with, what you expect for the frequency spectrum is some kind of delta, very narrow around the driving frequency. For in our case, it's 70.5 kilohertz. But that's ideal. That's happening if you're doing a long acquisition, because in reality, what you do is a short acquisition of the signal, and because it's a short acquisition, actually you don't have a very good frequency resolution. And in our case, considering our quality factor as a typical acquisition time are about 1 millisecond. So now if you start from here and turn on the jammer, well, this is basically what you get. And I think it's important to see here that the jammer is absolutely not tuned to meet the frequency of the linear Pmods. It's nearly 5% away from it. And even though it's away, it's still completely floating the information transmitted by the emitter. So of course, it's chaos. It looks like noise. So basically, if you make a longer acquisition, you can average it down, and then you have your linear signal coming up. But basically what it means is that if you want to see your signal, if you want it to be, for example, in this case, 3 times the standard deviation, well, you need to make much longer acquisition time. And this could be quite important depending on the application. So for example, if you think about self-driving cars, I don't think they use Pmod. I'm not sure, but they use some tough measurements for some of their probing systems. And if just beside your self-driving car, there's another self-driving car using the same kind of technique, but this one is actually hacked so that they will send this chaotic signal toward your car. Well, you might come to an accident or something similar. My point is just to say that with a device that was not made at all for chaos, we could completely blind another signal. I will go back to Pmods shortly after. Let's look at another application, which is the first one I told you about, true random number generators, which are used kind of everywhere. Here are just a few examples. I think the most important one remains secure transmissions. So basically what you can do with a chaotic system is to just look at what it's feeding you and convert this into an A-bit signal with some sampling frequency. And in our case, if you consider just the 3 last significant bits, you can have a complete random sequence. So far I was just talking about amplitude, but it's a resonator, so there's amplitude and there is phase, and the phase also is chaotic. So basically you have 2 signals with one device. And so you have 2 random sequences. And what people have found is that if you have 2 random sequences and if you mix them with a logic XOR gate, you have another random sequence, but with which randomness it's much better. And so we use this technique to try to see how efficient this random number generator was. And to do this, we run the test provided by the NIST. It's a quite famous test, and basically if you pass them all, then you can say that you really have an interesting true random number generator. And it starts to get interesting when you realize that we made this from a Pmod, but we can make it from double-clamp beam, a cantilever, a gyroscope. You can basically make it with everything as long as you drive it hard enough with some modulation. So basically what it means is that you could use the half dozen MEMS that you have in your smartphone to provide better security for data transmission, for example. And if you combine this with Pmods, thinking that you can maybe change the shape of the burst pulses, shape that would be every time different, so that you have a unique pattern every time, you can start to think of some interesting airborne wireless secure transmission. Okay, last application I wanted to talk about. So it's not yet done. It's in the future, but I think it's maybe the most interesting one for now. It's hardware cryptography. So here I'm not talking about creating a secured key. I'm more talking about something similar to what's happening in the quantum world. So as you probably know, quantum computers are getting more and more famous, and they do more and more stuff with this. One of the things that they aim at with quantum technology is to have a very secure transmission relying on quantum physics that is supposedly unbreakable. And they already used this for some specific data transmission, international data transmission. But the issue is it requires big equipment. It's very expensive, so it's not for everyone, actually. Another thing that quantum computers are interesting for is the fact that they can very easily find prime numbers. And you might not know, but prime numbers are like the core of a big part of nowadays cryptography. Nowadays cryptography has some algorithms that are based on the fact that we can't easily find prime numbers, and with quantum computers this will become much easier. So basically it will create some security issues. Of course, there are some other ways of doing cryptography, but if one way disappears, maybe it's time to create another way. And with chaos, there are new possibilities, And that's what we're going to talk about for the last few minutes. So if some of you are not wondering what's happening here, so usually when you talk about secured transmission, you usually talk about Alice that wants to send a message to Bob in a secured fashion. So for the purpose of this demonstration, let's say that Alice and Bob both have a MEMS in the chaotic regime. And what's interesting now is that if Alice sends a portion of her signal to Bob, well, his own MEMS will get synchronized to the one of Alice. And by synchronize is quite interesting here because we can think of synchronization for periodic system. Here it's a chaotic system that will be synchronized, which means that the amplitude, the phase, everything will be identical. There is only one thing: both MEMS needs to be really identical twins. So frequency, nonlinearity, damping, everything should be really, really, really similar. And when it does, then if Bob knows how to play with it, he can synchronize the exact same response, even though it's chaotic, to Alice's MEMS. Okay, so now let's say that Alice wants to share an information to Bob, some bits, some ones and some zeros. So what she can do is to control one of the parameters of the MEMS. For example, the resonance frequency, the easiest parameter most of the time. And what she can say is, well, if I want to send a 0, I do nothing. If I want to send a 1, I will change my resonance frequency to some ppms. Bob does not know of this. What he will see is that sometimes it's synchronized and sometimes it's not. And from this, he can deduce that he has the ones and zeros. Now there's one last character, which is Eve. Eve wants to know what's happening between Alice and Bob, and she also has a chaotic MEMS, but she has no clue of what the parameters are for Alice and Bob. So it's kind of a fake twin, and whenever she will be coupled to this exact same signal, well, she won't be able to synchronize it, and she won't be able to decrypt anything. So the main idea with using MEMS devices here is the fact that on one hand, it's really a model system. You can predict very well what kind of chaos you can have, and you can explore some very new stuff. And that's very difficult, for example, in optical systems, which are by themselves already quite complicated. And the other interesting part is the fact that, well, it's small, it's cheap. It could be very interesting to use these MEMS devices for IoT security, which is one big issue nowadays. So that's about it. I've shown you that from a micromechanical resonator, you can reach this stuffing regime, and from that, you can have chaos from basically any vibrating MEMS. And this chaos can be seen as a noise-like signal. And with this, we've trying to do some jamming applications and some random number generators for data transmission. So that's about it. If you want, I can also show you then how do we characterize such complex feature, but maybe first I let questions if you had ones.
Okay, thank you for a very interesting presentation.
Very nice.
Okay, so the session is open for questions. Please just unmute yourself and ask the question.
So this is Janusz Bryzek. How close the performance of these MEMS devices need to be in order to enable this type of synchronization that you are showing? 0.01%, 1%, 10%? Typically, you don't have too good reproducibility of like a high Q or whatever.
I agree. I agree. Indeed, it's one of the big issue of these kind of applications. So basically, depending on the parameters, the answers is different. And the very nice thing, so far it's, for me, it's mainly be simulation. I have not been able to test it, but from the simulation, it's quite obvious that damping is not a limiting factor. It's basically it's only smallly it does not depend much on the quality factor. If the quality factor is similar to tenths of %, it's good enough. The frequency, on the other hand, needs to be very close from one to the other. So of course you need to have access to the resonance frequency, either with some electrodes around, but the fact that it's very dependent on the frequency is also what makes it interesting, because if you had two devices that were not so close and that would synchronize, the problem then is, well, it means that basically you don't have many configurations, you don't have many keys. But on the other hand, if it's about a few ppm and that you can change your frequency of up to 10%, from ppm to 10%, then it means that you have a lot of possibility, a lot of configuration, a lot of different keys, and therefore a much better security. I cannot hear you anymore.
Sorry, I muted. So another related question. So the current generation of MEMS devices in mobile devices is not going to work because you cannot force them to drive into nonlinear mode. So probably you need a new generation of devices, correct?
Well, basically, yes, you need enough power. That's something that is true. You need enough power. Then it also depends on what kind of devices it is. So, for example, the example I gave was with a Pmot, and Pmots are known to have a very low quality factor. And because of this, you need to drive them really hard, because to go to the nonlinear regime, basically, it depends on what is your quality factor. But if you now get some other kind of devices, such as accelerometer or gyroscopes, quality factor is really big, and then it requires less power to reach this stuffing nonlinear regime.
I was just looking at the potential for changing all the iPhones to enable additional encryption, right? So a new type of chip. Technology that would have billions of applications.
So if you're talking mainly about the last application, then it's a bit different from what I've shown before, because what I've shown before basically says that you can take a device with a given application to meet some new specs. But if the point is really to make cryptography, then you could go back to these buckled doubly clamped structures, because anyway, the whole point will be to do cryptography. So maybe you can think of a specific geometry for it. And then buckled structures, if it's well controlled, and I repeat, well controlled, you can have very small buckling, but large enough to have chaos. And then if the buckling is not too strong, it doesn't require that much energy to jump from one state to the other.
Okay, thank you.
Very interesting, thank you.
Marshall, I have a question, and I might have missed this during the talk, but since you mentioned that the systems are exponentially sensitive to initial conditions, I mean, like that sort of like suggests the idea that a little bit like a seed in a random number generators. So is that the idea in the cryptography, that you exchange the initial condition is essentially the seed, and then that allows you to actually decrypt the signal that's coming from the MEMS device?
So this last application would actually require a talk by itself, I would say. This property of synchronization is really something specific to chaos, and it's not just as this seed that you're referring. It's a bit more complex than this. The main idea is to think of this chaotic system as some free. It is kind of free. It's a free system, just like an oscillator. It can move around. In an oscillator, it's in frequency. In a chaotic system, it's in amplitude and phase. It can move around. And the fact that it can move around, and that relates to what you said, the fact that it can move around, and on the other hand, it is very sensitive to any change, means that if you know how to deal with it, you can maybe do very small changes so that it changes the whole dynamics and collapse into some other's dynamics. And that's kind of the spirit of Bob synchronized to Alice. It's the fact that it will feed a few energy inside in a given way, and it will slightly perturb its own chaotic MEMS in such a way that it will collapse to Alice's one. But it needs to be constantly receiving this output. It cannot be just a trigger at one point. It has to be in continuous mode. And that's the reason why Alice can then encode information by changing, for example, the resonance frequency of the device, and Bob did not change anything, so he sees, oh, it's not synchronized anymore because the two devices are not twins anymore, and that's how he decrypts the information.
But so do you need two channels for that, like both like a public channel and some other channel to share?
No, so you just need the public channel, but you need something else, but this something else is common in most cryptographic applications anyway. You need Alice and Bob to agree on what is the configuration initially, how they become twins. That's something that you need to agree on. But the thing is, this is already what's happening in cryptography.
But that's more than just initial conditions.
Yes.
Yeah, okay. Well, that's pretty interesting. And I suppose you can study all of that in simulation.
Yes, so the interesting thing, and to me it's very interesting also for the application, you could think that simulation is good, and then you can basically, you don't need to have a MEMS. You just have a computer, you run simulation with what's fed from Alice. The thing is, chaotic simulation takes time. It takes a lot of power consumption. And if you start to have complex chaotic system, basically it takes much more time to simulate it than just to have it physically. So yes, for very simple system like the one I showed you, I can simulate and I can try to understand what are the limits. But at some point, only the device will give the answer, because it will take too much time.
Thank you.
There is one question from the chat from Anna. Would the MEMS chaos characteristic be affected by the fabrication process? Example, such the twins can be created?
So, yes. Basically, if how can I answer this easily? Yeah, let me go back to. I can't see my. Sorry, I did a mistake. I cannot remove. Oh, okay, that's okay. Yeah, that's good. So let's go to here. So yes, the answer, the short answer is yes. It can become very problematic. So the main idea is to be able to create two devices that are kind of similar, not really twins, just similar, and to have a way to control some of the parameters. And as I said, the damping is not so much of an issue. The frequency and the nonlinearity are very important. And it's a good thing that those two parameters can be controlled afterward from an electrode or some other things like this. And then you try to match your two devices to the same configuration. And the one thing I wanted to talk with this is the fact that you can park in different places inside the hysteresis. You will have chaos in all these places. And as far as you're concerned, when you look at it, it seems the same. But it's actually really different things, and only the other MEMS can see it. So it's not like if you shouldn't think of it as, oh, it's obvious the chaos is not the same. No. It's really, you can't see anything at all, and it's really something that comes from the synchronization process. But yes, to answer, it has to be very well controlled.
I have one question, I guess a fundamental question. You mentioned before, for the Duffing phenomenon, how you generate chaos, you modulate the input signal through frequency modulation, and then you said that the rate of modulation will affect you how much chaos the system will generate.
Yes.
And you said that is limited by the sensor of time constant of the Duffing phenomenon. What is that from the physical point of view? What is that limitation coming from?
Yes, so that's a very interesting question. So at first, the easiest way to think of it first is to just think of the time constant of the system. Not even thinking about the Duffing regime, just the typical time constant of the system related to the damping, the dissipation, or whatever. You keep this time constant in mind, and basically, if you put a rate that is of the order of this time constant, then you are out of equilibrium, because it doesn't have time to settle down to one of the two states. And before it understands that it should jump down, you're already asking him to jump up, and so on and so on. So if you're just within this regime, you will probably have chaos if you're parked in the right at the right frequency. But that can be understood. It's not too fast, it's not too slow. What becomes interesting is the fact that if you increase the size of the hysteresis, you can basically increase the rate as well. And this, to me, is still unclear, because even though the hysteresis increases, this does not mean that the time constant changed. So for example, if you were in very large Duffing regime, you're parked in this hysteresis and you shut down your drive, it will take the standard relaxation time to go to low amplitude, even though it was a very large Duffing and everything. Thing is, it seems that when it comes to chaos, we were able, so for example, here the bandwidth is 800 Hertz, and we were able to do modulation up to 4 kilohertz, so five times more. And what this means is that we have a broader frequency spectrum. So it's really increasing somehow the bandwidth of the system. But it's related to the Duffing regime, but also to the fact that we are in this chaotic regime. It's not totally clear for me so far.
But if I understood well, basically, as far as you are within that nonlinear region within the Duffing, or unstable region, then you will create chaos.
Yes, roughly speaking, yes, clearly. It's basically, that's the idea, yes.
Okay,
Yeah,
thank you.
I have one more question here. This is Willie Picken. If you've got an 800 hertz bandwidth, you're around about a 1% information bandwidth that you could use for the system. Do you see that as being typical? Because that's not really enough for a communication system.
Can you say again, because there is some
noise? Okay, I'll
yes.
try. So if you've only got an 800 hertz bandwidth on a 70 kilohertz signal, that's about 1%.
Yes.
So your information bandwidth that you're sending on the system is about 1%.
Yes.
But I mean, you can even some wireless can get away with that, but most communication systems would be wider band than that.
Yes.
Do you see the relative bandwidth as being a constraint of chaotic systems, or is it quite feasible to have octave bandwidth systems?
Yes. So basically, if the goal is to reach for example, telecommunication, clearly chaotic optical system will still remain the best solution and will provide basically the full bandwidth that you would require from optical fibers. For MEMS, of course, it's completely different. We cannot reach a terahertz frequency. Here, it was a Pmot working at 70 kilohertz, but MEMS can vibrate up to gigahertz with BO, for example. I agree with you. Nevertheless, it will be still a few percent of the vibrating frequency. That I completely agree with you. But basically, the idea is not at all to try to reach to the highest possible rates, is to try to reach to the good application. And when I mentioned here IoT, it's not for nothing. It's also because a big portion of IoT communication is just like 2G, so basically a few tens of kilobits per second, not more. And they don't need more because it's not so much data. It depends, of course, on the application, but most of them don't require so many data to be shared. They require to be securely shared. And so that's basically what we are targeting. Does that answer your question?
Yeah, that makes sense.
Okay, one last question, if any. Okay, I think we can stop here. Let's give a virtual applause